Welcome friend. Today we are going to study the singly reinforced beam, singly reinforced section. So, in singly reinforced section, let me just give you the brief that what is the RCC. So, basically, if we have cross section of a beam in the bottom of the that section will provide the reinforcement, right? Reinforcement, and that reinforcement is called as the AST, that is area of steel in tension. So and this is your neutral axis. So upper portion, if the sagging moment is there, then upper portion is under compression and bottom portion is subjected to tension. So in the singly reinforced beam section, if we draw the that diagram of this stress and strain, then it will be something like this. Here it is 0.0035, and this will be Fy upon 1.15 es upon plus 0.002. So this is the strain diagram, and if we plot the stress diagram, then it will be something like this. Some part will be rectangular and remaining will be parabolic, and the value is 0.446 FCK, and this is the force that is the C force that will act at the center of gravity at the distance of 0.42 into XU, where XU is the depth of neutral axis. Similarly, we have the T over here. So I think you are aware about that C will be 0.36 FCK. This is the stress into D, that is the width of the section, and B into XU, that is the section under the compression. So B into XU. Similarly, T is the 0.87 into Fy. Fy is the yield strength, 0.87, that is the strength into the area, that will be the AST. So mostly we provide the area of steel, the effective depth of this beam in such a way that your C will be T, that means it is balanced. Whatever the compression is registered, same will be the value of the tension. So if you put this value over here, then it will be 0.36 FCK. B into XU is equal to 0.87 Fy to AST, Fy into AST. So if you just take out this XU, then XU will be 0.87 divided by 0.36 FCK into B, this one. So this is the equation given in the annexure. So first of all, for the problems of the analysis, there are two type of the problem. One problem is called as the analysis of the section. So in that you draw the figure, then you find out the AST, then you find out the XU and XU max. So XU will find out through this equation, and XU max, this is the note given in the code 456 and page number 70, right? On page number 70, this note is given. If your grade of steel is 250, and then your XU max will be 0.53 D. Indirectly it is a XU by D, that will be 0.53. If you are using the 415 grade steel, then it will be 0.48, and 0.46 for 500. So this is how you will find out the XU and XU max. Once you have the XU and you have the XU max, you compare these two value. Either it will be XU is equal to XU max, or XU is less than XU max, or XU is greater than XU max. So if it is XU is equal to XU max, then it is a balanced section. If your XU is less than XU max, then it is under reinforced section. And in calculation you have to consider the XU max is equal to XU. And if your XU is greater than XU max, that is what called as the over reinforced section, and in which you take XU is equal to XU max. So once you have the section, whether it is a balanced section, whether it is under reinforced section or over reinforced section, so this type of question may be asked in the section over reinforced section. XU is less than greater than XU max, XU less than XU max. This type of question may be asked in the examination. Then we find out the how much moment that section can resist. So if you have the balanced section, then we consider this T into Z. So let me see what is T into Z or C into Z. Now see, here you have the two force, one that is a C force, another one that is a T force. This is a C and this is a T, and distance between these two couple force is Z. So see, overall depth here, this depth is capital D. So capital D minus this 0.42 XU, that will be the Z. So here that Z will be D minus 0.42 XU, right? That is your Z, that is lever arm between compressive force and tensile force. So T and Z. Similarly, see here Z is given D minus 0.42 XU. This is something like that, that is the C, and here you have the T, right? This is your C and this is your so from the top of the compression fiber, the distance is 0.42 XU, and from the top of the beam, the location of T is D. So distance between this C and T, that is D minus 0.42 XU. If you have the under reinforced section, see, if you got this XU less than XU max, then you go for this calculation. If you have XU is greater than XU max, then you go for this calculation. So if you have XU is equal to XU, then XU max, then you go for this calculation. So for under reinforced section, we find out the moment T into Z. For over reinforced section, we find out the C into Z. So as you know, T, what is T and what is C and what is Z. Then we find out the limiting moment. So for limiting moment, equation is given in SP16. That if your Fy is 250, then that will be 0.14 FCKBD square. So you find out this value of mu for relative grade of the steel, and then we compare the mu and mu limit. So if your mu is equal to mu limit, then it is a balanced section. If mu is less than mu limit, then it is under reinforced section, and if mu is greater than mu limit, then it is over reinforced section. And then we find out the percentage steel equation, right? Percentage steel. So PT will be find out by PT will be considered as a PT is equal to 50, then FCK upon Fy bracket 1 minus under root 1 minus 4.6 mu upon FCK B into D square, right? So this is